So Lauro is going to make a presentation on something that we've been working on WPEWebKit, which is called Profile Guided Optimizations, which is, in a nutshell, is basically getting some profiles and adapting them to the specific use cases to improve performance. But Lauro is going to talk all the way about it. So Lauro, when do you want to start? Feel free to do it.
Okay, thank you. So good morning, everyone. And it's a pity that I was not able to be there to meet you all, but let's see a little bit about the profile guided optimization now. So a little bit about me, as usual. I have been at Tigala since 2020, working mainly on QA and the WebDriver, part of WebKit. In the past, I also worked on the Enlightenment Foundation libraries, mainly also on bindings and on the MyMO distribution from Nokia. So it will be a short talk. We are going to see a little bit about what motivates us to seek techniques like profile guided optimization, a little bit about PGO itself, some slides about the profile data that we need to collect, etc. How we implemented it in WebKit, and some results from the tests, and what should be the next steps. Okay, as you can see from probably everybody attending the Hackfest already know, the browsers are huge. And they also nowadays run very large software. JavaScript of a few megabytes, and keeping the compatibility between different versions. Page from the 90s should still handle today, and they must run everything as fast as possible, as usual, because the user usually are not so patient, and also because we wanted the user to have a good experience as close to the native application as possible. For that, we have on top of actual work on the software that's running on the browser itself, and the browser itself, we can seek help from the compiler with optimization flags like 02, 03. And internally also the compiler has a lot of risks to optimize different paths of the code. But especially on generic software like browser engine, they are not crystal balls. For example, we can build WPEWebKit, and we will be used to run plotting in a shopping mall, displaying some ads with some browser more focused on multimedia, TV play, video play, or for games, or on a generic browser to navigate. So depending on the kind of the workload that we have to do, those risks could be either a hit or a miss. And what if we could help the compiler to understand what will be actually running on the end? So in this front, there's a technique called profile guided optimization. Also, some people know as feedback directed optimization. There are other names like instrument and directed optimization, and they all have in common this idea of providing the compiler some information about the real use use cases of the or workloads of the software that will be that it will generate, instead of just trying to guess from the risks or other annotations like those unlikely likely attributes. We provide real world data, and then the compiler know, okay, this, for example, for branch prediction, it can detect that, okay, this body of the if is not a hot path, so we can just move it away and optimize. Also help with inlining, deciding when to inline a function or not. Or for example, also PGO works. It's often used in together with the LTO, the link time optimization. Both are in Clang. They work kind of, let's say, in some way, sibling optimizations. And PGO, it's a relatively low-hanging fruit to enable, but if we do it right. I mean, it's a low-hanging fruit in comparison to more intrusive approaches like the refactoring, large refactorings of the code, because usually PGO doesn't require any changes on the code, so it's easier to enable. So basically, it's like the compiler asking, what do you want me to optimize? Let's I think it's like the option like -o what, and the first step is to collect some profiling data. And it's important that this data must be representative of the workload that we'll be doing. For example, if we have some, let's say, a graphical application that draws a given type of primitive instead of going to a, let's say, a legacy or other kind of primitive, and we end up using the wrong workload, the compiler will be generating code that when the user runs, will get a lot of cache misses and jumping around, and it will not perform very well. And also we get this good set of profile data we can feed back to the compiler, and the compiler will use it to generate the actually optimized software. And then we can get hopefully, the improved performance in the end. So currently, we are going to see better in the next slides the WebKit details, but this talk is mostly focused on Clang. So in Clang, for PGO, we have basically two ways of creating the gathering, I mean, the profile data, which is instrumented builds and sampled data. For instrumented builds, we have this option of compiler front-end profiles, which is better aligned to the source code, but it's more expensive, so it's usually more used for test coverage. And for PGO, what Clang recommends is to use the IR, intermediate representation instrumented build, which has low overhead, a little bit lower overhead than the compiler front-end one, but it's still more overhead than the sample using a sampled approach, like using path data, because it has the lowest overhead. But the drawback of using the sampled data is that for sampled data, for example, you can't mix with data from instrumented builds. Let's say that you use a given workload with an instrumented build and you have sampled data from another build. You can't mix them to create a unified profile. So it has this limitation. And also the sampled one, you might have lost some coverage because it relies on statistical snapshots. For instrumented builds, the compiler, as mentioned, they inject some code into the final binary. For example, Clang uses the compiler RT library to help with this. And it's possible to use some partial instrumentation, like, okay, just instrument these files, those functions, which makes, for example, you could create a scheme where you profile just the model that was modified in a given pull request in CI instead of doing a full instrumented build. And while the software is running, this injected code is collecting statistics about the function calls and this kind of information. And then we have this injected function LLVM profile dump that writes back the collected data. By default, it writes in the @exit handler, which is a problem, as we are going to see in WebKit and multi-process application, because you need to ensure that the shard process and the main process they exit cleanly to be able to to save the collected data. Clang has support for a continuous collection mode, but the last time I checked, this was supported only on Darwin and not yet on Linux. So it's not an option. And it was something that we need to pay attention. And for example, you might have a CI system that kills the browser instead of gracefully calling sigterm, for example. A bit more graceful. Also, this profile data is compiler specific. We can't mix GCC and Clang builds, instrumented information. They are usually collected as with this extension, prof raw, and then we use the LLVM prof data to merge into a unified profile. And this LLVM prof data allows us to inspect the profile data to check the number of functions that, for example, in this run from, I think it was a motion mark run, there were 250,000 functions and instrumented, so it's a lot of data. I think the full WebKit run in a build was a single profile was about 50 to 60 megabytes. And also this command LLVM prof data show top N20 shows the functions that used most, that were called the most in the code. that has more samples, larger internal blocks. Yeah. Okay, now, as mentioned before, the profile workload should be representative, and exactly as it should be representative of the actual, let's say that the intended workload that the user will do, we need to be careful with using unit tests because they often test just the exceptional part of the code. They don't give the right relevance to the actual normal use case of the software. And if we have different scenarios, for example, a regular browser, like in WebKit we have this formula for collection, which uses 6% of the motion mark, 20% of the speedometer, and 20% of the jet string. Then you can balance and try to find the kind of profile that gives better results in the end. Yeah?
Yeah, Lauro, it's a 20 minutes thing, so if you can try to speed it up a little bit to
Yes,
also give some
okay.
minutes at the end. Thank you.
Yeah, the next slides are going to be shorter. So other things to keep in mind are related to cache of the results, because the profile data will be an actual input of the compilation, and then it must be treated as actual source of the code, which can give false positives. And we need to be careful of relying too much on PGO. For example, some expected fluctuation in the test, especially in complex profiles like in a browser, might give some fluctuation in the results and might hide actual regressions. So keeping testing without PGO is also important. So in WebKit, until recently, it was supported only by Apple ports in the Xcode builds, and in April we added support for CMake for WPE and GTK. As mentioned, it's IR level with Clang, and it's exposed as two CMake options: enable LLVM profile generation and use PGO profile, which receives the profile file that will be used. Some issues that we had while adding it was that the instrumented code, especially together with LTO, was that the instrumented code exposed some symbols. Then only for instrumented builds we had to allow to relax some rules. But given the instrumented build will not be used, let's say, for the will not be the last safety net in the tests, it should not be an issue. Also, we had to introduce some few changes in the teardown of the child processes that changes the code between the instrumented build and the final build. So it gives some of those warnings. But the main problem was the clean shootout, because the web process and the network process were usually killed with CQ during the browser teardown. So we had to add some handlers to manually save the profile data before actually killing if needed. And also to collect the data, we had to disable the sandboxes, because bubble wrap was interfering with this process of graceful termination. There were also some issues related to distributed compilation. which we had to use some options to ensure it worked for instrumented builds, but optimized builds still I was only able to make it work locally. So some test results. First of all, the test results that we have available are not statistically robust. They were originally done for guidance during the development, and it was based on a version of the patch before it was merged, but the patch did not change much. The essence is the same, and it was using different configurations like vanilla WPE, instrumented WPE, an LTO only build to check the comparison between the LTO and PGO and the LTO only. And they used different training data for just stream speedometer, motion mark, and a merged profile of the D3. So the instrumented builds were slower, as expected, from minus 10% to minus 30. LTO alone was often under 10% improvement. This is related to the scores because we built the optimize those versions and here run the benchmarks. And PGO on top of LTO was basically always improving the results. And the best case scenario, let's say, kind of cheating in a way, was, for example, using the motion mark training data to optimize a build and rerun just motion mark. But the good thing from those tests was that the merged profile was, which is the most realistic option, was representative enough to keep a good level of improvements on top of the LTO one, and sometimes getting closer to this overfitting, let's say, scenario. So for the next steps on this front, we are talking about checking how can we enable PGO in the WPE and WebKit CI so we can properly track the performance improvements on the main benchmarks. And for the end user, something that came to my mind was, for example, enabling Epiphany version with profile data with PGO support for testing. We also want to properly measure PGO embedded boards and check other kinds of measurements of profile like partial profile and sample based profile, which makes it easier to collect the data. So the main takeaway is the PGO. It's seems like a good tool to optimize, and large code bases like WebKit seem to benefit from it. We saw that some years ago Chromium already uses it with good results, but it's not a silver bullet. So we need to be careful and conscious when adding it to our builds. So few minutes for discussion. Sorry for the rush in the end.
Okay, thank you, Lauro. Is there any question or comment? Yes. Yep. Oh, you have the one there. I think you can use it straight.
Hey, I only wanted to ask.
Can you get it closer?
Yeah. You mentioned the PGO and the process pre-warming. I didn't catch all the issues you mentioned there. Could you maybe elaborate more about those issues? It seems quite interesting.
Sorry about PGO and
Process pre-warming. web process pre-warming.
Sorry, no, it's not pre-warming. It was more. Let me switch. I think it was.
Or maybe I misunderstood. Yeah.
I think it was this one. The mention about web process network process was more related to the teardown of the process when the browser closes, because this feature of because LLVM profile dump runs on the at-exit handlers. The default way in some scenarios when the browser was closing was to just kill the children, and then we lose the profile data by default. So we had to add those handlers to ensure that we save the data.
Okay. Thank you.
Thank you.
Okay. Any other comments or questions? Local or remote? Okay, so thank you, Lauro. Thanks for your presentation. Oh, sorry. There is one guy here. You will recognize him.
Lauro, one question. I saw the percentages that you used. Can you hear me?
Yes.
I saw the percentages that you used for deciding the weight of every benchmark when doing the PGO. Did you try any other percentages, or was that like the default some place that you found it, or because I had the feeling that I talked to Justin a lot about this, that the speedometer probably should be kind of a little bit higher, I guess. No?
Yeah, for the tests that I run was before checking this formula. I think this formula is on some PGO scripts in WebKit that we are not using yet. So this probably is optimized for a generic, maybe desktop browser or something like that. But it's something that we can play with the actual workflow that we want to address.
And is that hard-coded in some place in our infrastructure, or is something that you need to add somewhere?
I think it's hard-coded, somewhat hard-coded in a few scripts inside the two scripts inside WebKit. I think it's from the some Apple scripts that they have for PGO, because I'm still starting to check how those scripts run. How can we use, because so far the approach has been a little bit to a bit more manual way to enable PGO and so on.
It has to be super quick because we are already past time. Okay, so yeah, if you have more questions, Laura is not here, but he is connected to the WPE matrix room, so you can also ask them.
Yep.
Okay, thank you, Laura. Thank you. Now
Thank you.
we can clap.